Welcome back, Mr. Nichols here again, looking at solving a horizontal accelerated motion type of problem I call the stopping distance, or can it stop in time type of problem. I thought now would be a good time to introduce you to Hoover Cat, who's kind of my official mascot when I teach physics here. She's a rescue cat that I got more than a few years ago, who has kind of a never-ending source of inspiration, and she makes me laugh when she doesn't bite me. That's a whole nother story. With the stopping distance problem, it's all about the setup. So let me kind of explain what goes on here. Okay, I'm just going to kind of grab this guy because I kind of made this up specifically for this one. So here's the setup. Yeah, it's kind of a funky little car there, huh? Yeah, I like that. Especially with the Pro Mod hood scoop there. You wish you had that car. The setup is as follows. You're going to have an object that is moving. Car, bus, train, something. And at some other point, there's going to be an obstacle. Just something. It's like, hey, I'm an obstacle. It could be a tree, a moose in the road. It could be a bridge that is out. It could be a tree that's downed across the road. It's physically something that will impede the motion of the object and is in line with it. So typically what they're going to do is they're going to give you this. They're going to give you the distance away that the obstacle is from the car when something happens. So typically it's going to be, you're driving, oh gee, something's in the road. Well, you can't avoid it. Slam on the brakes. So now you're stopping. So it's a stopping distance problem. So what that brings in are a couple of things. Okay, you want to keep in mind that we're going to have the car moving at a certain rate. So it's going to have an initial velocity. Now, in order to avoid hitting the obstacle, it is going to travel all the time. It is doing this. It is decelerating. Let me try that again, probably with, that's a little better. So you have a deceleration, which means the acceleration is a negative acceleration. It is slowing down the velocity. Now here's some applied physics here. The deceleration of the car is produced by the brakes and what you have in the brakes. So we're talking about the brake pads that you have, and we're talking about the brake rotors that you have. Physically, that determines how much force, clamping force, can be applied to the tires. So with better brake pads and better rotors, the car can stop with a larger acceleration rate. It will stop in a shorter distance. Now, if we assume that when you hit the pedal, you can't push any harder, and with all cars today being ABS, you're going to get the stuttering wheel lock that happens as the car tries to prevent a skid. So you're going to get maximum braking from your effort and the pads and the rotors. So that is something that is directly tied to the car, that deceleration rate. The velocity of the car is directly tied to the car. Now, ideally, we want it to be stopped before it hits the obstacle. So the deceleration will cause the car to stop. At some point, it's going to stop. If we forget about the obstacle, we just want to figure out how much distance does the car need to stop. Now, the obstacle's there, but keep in mind that this does not govern the motion of the car. So it is not the displacement of the car. We're going to use it as a comparison value when we solve a problem. And that's the kicker here, is you're not going to use that distance. Okay, that is the one thing that is not part of the problem. Everything else is associated with the car. So that determines the motion of the car. So here's the problem. This is one of the ones that you've looked at. I believe it's A16. We have a Porsche traveling down one-lane country road. Okay, 27 meters a second. So that's, I'm gonna keep my eye on that right there. Travels around the curve, large moose standing in the road 40 meters ahead of him. Okay. Moose are big, and if you hit them, you get hurt, moose doesn't. He walks away, usually. The maximum deceleration of the car, not the braking system. Determine whether or not he can avoid a crash. So think about what that means. That means car is here. M is moose. You need the car. You want to figure out, is the delta x, is the displacement less than the distance to the obstacle? So let's work this out now. Let's ellipse it out. Faster with the eraser. Yeah. So let's lay this out. I'll keep it to a nice subtle color here. Knock it back to, say, that font. Traveling down the road at 27 meters a second. Okay, well, guess what? It's the right base units. It's 27. That's about highway speed. That's cooking pretty good. It is a Porsche, though, so we'll let it go. Now, the temptation might be to do this. Delta x equals 40. No. No, 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 no. That, when you put it there, that says the car stops in 40 meters. It doesn't. We don't know where it stops. We know the braking system will determine where it stops due to the acceleration or deceleration. So that's the wrong thing to use. So this is just going to be a question mark. Now, we want the thing to stop. So it's a stopping problem, so we know the final velocity. We want to figure out how far it travels by the time it gets to 0. Here's the kicker. It is a deceleration rate. And if you can read by all the junk I just highlighted there, the acceleration is a negative 8.5 meters per second squared. The base units are good. It is decelerating the car. The sign of the acceleration is opposite to the sign of the velocity. I didn't pick a sign here, so it just says 27. That means by default it's 27. Slowing down an object always has opposite signs like that. So determine whether or not he can avoid the crash. Well, a couple different ways to do it. Let's do it the way a lot of guys may tend to do this initially. Say you don't immediately see how to do this with the equations that we have above here. Say that you said, I want to figure out the time it takes to stop. Okay, well, let's start with that one. So VF equals VI plus AT. This will tell you how long to stop. So we know we want it to stop. We're moving at 27 meters a second. We are going to lose 8.5 meters per second every second the car is traveling. So you're seeing this is 8.5 is almost 9. That's 27. It's going to be about 3 seconds. Let's do the math. Negative 27 equals negative 8.5 times t. Divide by negative 8.5. You get a positive time, which you better get. And I'm going to crunch some numbers really fast here. I get 3.18 seconds. I'm going to put that right there. Now, let's open up a little more room. I want to know displacement, so let's go with the go-to equation. Delta x is VAV times t. The average velocity, 27, cut it in half, 13.5 meters per second. The time to stop this vehicle is 3.18 seconds. This will give you the stopping distance in meters. So 3.18 times 13.5. I get 42.93 meters. So the car hits the moose. So basically, just don't write the number down and just say that the problem's done. Speak intelligently and say, what does the 42.93 mean? That's the first method. Now, if you want a faster method, let's go back here and say, well, it's not asking me for time. And if I can get displacement without solving for time, let's do that. Well, let's look back here. If we look really closely, We've talked about this equation being linked with stopping distance. If you know the velocities and the acceleration rate, you can figure out the displacement. So let's go back over here and do that. So I want to know what the displacement is going to be when I use this information. So again, this is my equation. This is my E. There's my L. This is my E. My plug-in comes next. It's going to stop. The initial velocity is 27 squared. The acceleration is a negative 8.5. And this will tell me the displacement, the distance it takes to stop the car. 27 squared is 729. Bring it to the other side. Negative 729 equals negative 17 times delta x times the displacement. Last step. Divide by negative 17. 42.88 meters. So crash. Probably about the same as the last answer. With round off, it's going to change. But this type of problem you're going to see time and time again, usually once on every page. The first page, A15, it was the shopping cart, and will the shopping cart stop before hitting the row of cars? There was the moose in the road. There's going to be someone driving a BMW on the next worksheet, and can they stop before they reach a crosswalk? It's going to follow the same pattern, guys. Typically, the distance they give you between the object and the obstacle is not what you put into the equation. It's what you use as a comparison. Okay. The deceleration is linked to the car. That will dictate, along with the initial velocity, the stopping distance of the car. It's like having a paint mark in the road. Will you stop before the paint mark? It's just there as a check. So this problem typically does cause some challenge because a lot of guys will plug in the value of the object separation and they'll get a number. It's just that sometimes the number may not make sense. So the way I'm showing you here is you will always understand the answer. If you try to solve for whether or not the object's moving has a final velocity greater than 0 at the point of collision, that's a whole nother way of solving. But I wanted to show you this one. This concludes the mini lesson on stopping distance or will it stop in time problems. I hope this has been helpful. Thanks a lot, guys. And let's say goodbye to Hoover. Okay. Goodbye, Hoover. Goodbye. I'm hungry.